Hello everyone, welcome to the fourth lecture. So for this part we'll specifically go into evaluation metrics, evaluating machine learning systems and data science practices in general, and then we'll get a bit into generalization, which is a very important topic in machine learning, so is also very much applicable for data mining. We'll discuss how to set up for good generalization, being somewhat skeptical about our data, about our target, and our algorithms. And then at the end, we'll go into a real example to sort of show you how these things play out while you're actually doing a prediction task. So let's first look at evaluation in practice. Now, just to remind you why we're actually doing evaluation, remember that we have this function, which can be a classifier or a regression model, and we have our data input x, and we hope that this returns our target labels that accompanied these instances. And by training this function, we hope then to sort of generalize to new data so that given input, we can still predict the correct labels for these. So our data x is just a matrix. I composed it as a flat matrix here. And we have our true labels, which is y, and y consists of, for this example, binary values, so zeros and ones. It's basically a sort of list style object. And we have our model, which I here denoted as k and n. Now k and n, as you can see, has an input x, but also has a parameter. So case 3 is one of the parameters, and then this outputs our predictions. So note that this notation is somewhat different from this one, because this is our hopes for our objective, but this is essentially the real deal where we have our model and it outputs our predictions. So our predictions have this special notation with the hat, and then you can see that here we also have a bunch of predictions that are also all binary. Now, given these few objects that we have, and especially y and y hat, we need to have some sort of sense of how our model is performing. So over the years, people have come up with these metrics to show different interesting aspects of our predictions compared to our original values. And note here that our model is our algorithm with our parameter settings trained on data. That is what we refer to as a model. Now, sometimes you might see that an algorithm and a model can be the same thing, but in essence, the classification algorithm or the regression algorithm, such as KNN or linear regression, is always referred to as an algorithm, and then when it's actually fitted on data, it turns into a model of the data. Now, this type of evaluation is not too different from statistics, which we can see by comparing the two. So for doing statistics research beforehand, we have some hypotheses or hypotheses. We collect our data, which is generally experimental data using people, and then we do some statistical tests on the data, and this test is going to show us some significance and effect size regarding the variables that we're comparing in that data. And then from here, we can draw some conclusions and either reject or accept the hypothesis. Now, when doing machine learning or data mining research, this is essentially the same. So beforehand, we have some idea that the data that we've collected has some specific target, and a target can be predicted using our data. So we assume that there's patterns in our data that are good for predicting the target value. Then we gather data. Now, we might do this from experimental research, but generally this is in the wild data that we collected somewhere. And then rather than one statistical test, we have our model that does predictions. And after it did these predictions on our data, we want to have, similar to a significance test or some effect size, we want to have metrics to see if our hypothesis still holds. And these might be baseline metrics or some predictions from another model or from our own model. But we need a bunch of those to compare and see how we're actually doing, because otherwise we can't draw any conclusions. So the important questions that we're asking is, did our model learn something? So is it not just making some random guesses? Is it actually picking up on patterns in the data? And more importantly, are we doing better than either a baseline, a previous model iteration, maybe some related work, or state-of-the-art research? But in most cases, we either want to prove that something is predictable better than a baseline, or we want to prove that a certain method works better than a method that has been explored before. Now, one of the upsides from doing this type of predictive research is that we can do formal comparisons. And what I mean by that is that in equal conditions, so equal data, equal parameters, and equal target values, we'll have exactly the same results, and we can just evaluate those with a bunch of metrics. Now, this is somewhat different from statistics because obviously, at least for experimental research, you are dealing with humans, and humans can vary a lot. They can have different behavior in between observations. You need to have a lot of them to have a representative sample, and even so, there might be a lot of external factors that you haven't measured and therefore might affect your final conclusions. Now, this is not the case for data mining / machine learning research because we only have these labels and that's that. However, that doesn't mean that we're free from any methodological constraints. Actually, it introduces a lot of others, and those I would like to get into today. So for the remainder, it's good to have sort of this visual image of these outputs that we have. So y hat, we have maybe some other model predictions, which I just noticed m hat here, and then some baseline predictions, which I call b hat. And the thing we're interested in is just this metric comparison between any of these to give us some sense of performance. However, there's multiple metrics for a reason, because not a single metric can capture your performance best. It's always good to look at a few of them, and also it's very important to look beyond these metrics. So the whole setup, the methodology is equal as important, if not more important, than these metrics we have at the end. But similar to p-values, these are the main sort of impact factor of the work that you're doing. So the higher the scores, the higher the difference with any previous work, the better it is for you. And therefore, it's very important that you are very skeptical about your results and always try to make sure that you have the best and the fairest setup you can possibly have to avoid overselling your work or having predictions that might turn out to not be as high as you presented them in the future, and all these kind of things. Now, as a first step for this, it's always important to pick the metric that fits the job. So for regression, we've gone into R-squared, root mean squared error, mean absolute error. Now, there's also a bunch of more metrics, which if you click the link, it will guide you to the scikit-learn website, where it lists a few more of these metrics. For classification, we've looked at accuracy, precision recall, F1 score, also at ROC. There's a few more. So for example, if your labels have to be ranked, so you output more than one label and they need to be in a specific ranking, there are some losses that are specifically interesting for example, neural networks, and a few more that you might see reported in any papers that you read. And as I said before, these metrics all have a sort of different job to do that will give you more insight into the predictions. Now, for most of these metrics, either the higher or the lower the better, but that does not have a very definitive say about the quality of your model or your predictions. So for example, with R-squared, it tells you something about how well your model fits the data, and if it is 1, you have a perfect fit. However, this doesn't necessarily mean that with a low R-squared you have a useless model. So even though your model has a very poor fit, it might still be able to predict things in a sense that is acceptable to your use case. So say, for example, we're trying to do biddings for either stock or maybe bids on auctions. We might be very poor at predicting things, but we still might make a profit using a certain model with a low R-squared score. And similarly, a high R2 score doesn't necessarily give you a useful model when, for example, you're overfitting or you're making incorrect predictions due to some bias. So your training data might have been perfectly fitted, but then for any new data that comes in, you're making incorrect predictions consistently. So therefore, you always need to review your R2 score in combination with any errors and a very good sort of evaluation setup. So we can, for example, look at mean absolute error that will tell us how far our predictions are off from the actual values that we wanted to predict. And for root mean squared error, we weight the predictions that we're off by a large margin very heavily because that's worse, or at least the intuition is that that should be worse. So again, you can sort of evaluate this thinking, okay, if I make a mistake that is twice as bad, is it actually twice as bad, or is it even worse, and do I need to have a even larger impact for the model when it makes very big mistakes? So depending on this, you would either go for absolute error or squared error. And remember that for both of these, the interpretation depends on your problem, it depends on your target. What makes a very big error depends on what you're predicting. So say that you're off by 1,000, that's pretty nice when you're guessing house prices, but it might not be so good when you're doing low value predictions for stock prices. So it's important to know what these metrics do and always make somewhat of an informed choice when trying to motivate for yourself why you're picking any of these. And for classification, we can basically just pose the same notes. So while accuracy is very handy for very balanced data and it gives you just one number, as we've seen, it's also very unreliable when you have unbalanced classes, and it's generally more useful when you have multiple labels, the classes are sort of equally distributed, and you don't really care about predicting a certain label. Now, in any of the cases where you do, this is where precision recall and F1 score have a very good addition to this single metric, and in any case, they will be way more informative than just raw accuracy. But keep in mind that when you move away from binary predictions, this sort of matrix that you have where classes are compared to each other in terms of precision recall and F1 score, it can get very tricky to interpret. And when you have to average them to get back to one single metric for all your classes, you have to take into account different factors such as, do I have unbalanced classes? Do I want to weight them with the frequency that they have to have a fair score? Do I just average over all of them? And it will therefore introduce a bunch of more choices. However, in the cases where you have a very strong preference for either precision or recall, these are obviously very good metrics to use. Now, I somewhat alluded to this before, but just to answer the question, are high scores everything? No, they are not. And why is this the case? Well, much like any results from any experiments, we need to check if the methodology was all correct and we can actually trust the results. Now, this is one of my favorite examples for machine learning gone wrong. There's a sort of image classifier that tries to predict what object is in an image. And this paper by Ian Goodfellow and others had this very neat setup where they tried to sort of corrupt the input image with a very nonsensical noise. So this signal over here in the middle is overlain to this is not going to affect the image that much that we can't distinguish it from a panda anymore. But as you can see, this model thinks after introducing this noise that the image is a gibbon rather than a panda. most notably with very high confidence. So introducing this sort of arbitrary noise that wouldn't hurt us as humans that much can really throw off these models. So it's always good to keep in mind that this is not super intelligent software, right? It often doesn't generalize the way that humans do, which is incredibly important to always keep in the back of your head while doing this type of research. And even though you're getting very high performance scores, it might still be that in some case your model becomes brittle and starts classifying pandas as gibbons. Now this is a very clear example, but when you're working on any of your own tasks, sometimes it can become somewhat tricky to stay very wary of the predictions that your model is making and keep this sort of healthy lack of trust in your predictions. But now doing this will overthrow your methodology, and it might be the case that you are unpleasantly surprised by the performance of your model. Now, for most academic settings, we only have a very limited source of data. There's generally, for a task, a very specific, popular set of data where, at least for machine learning research, most of the optimizations are tested on. But in industry, you generally have access to either a lot of data, you have access to a data stream. So on one side, this is an upside because more examples will generally cause better generalization, but there's also more on the line than just your reputation, because doing incorrect predictions will generally cost money. And apart from the impact that the predictions will have, it will generally also cost you a lot of time and resources if you're not opting for a good model. Because even when you have access to constantly new instances to retrain your model, if your predictions are always off, you have to retrain everything. That takes a while. You might have to go back into revisiting your methodology, redo your setup, retrain, etc., etc. And this will take a lot of time in general. So it's good to make sure that everything is set up as fair as possible, so that hopefully in the end you will end up with a model that you trust to some degree and you can deploy and have some confidence that it's not going to mess up in the long run. However, much like writing software, it's also important to try to debug or sort of attack your model with examples that you think it will fail on, that will be very informative to your further process, but also to your research or anyone that you have to inform on the performance of these models. So hopefully with this, I've managed to convince you why generalization is important, and we will go into some more specific examples regarding, for example, your data. Now, this is something I always like to stress. It's easily overlooked how important it is to really get to know the data set that you're working with. Especially when you're more into machine learning, it's very easy to just regard it as a set of inputs that you do a bunch of transformations on. You learn a model and you're done. But one of the problems is that your data might also be a cause of why your model is failing. Actually, it might be the most important reason why your model is failing. So we'll go through a few steps here that are sort of good advice. This is not an exhaustive list for any of these points I'm going to discuss, but at least it covers the general surface issues. So one of the first things to look at is the way that the data was collected. Especially if you're not doing it yourself, it's always good to be skeptical about people collecting data. They're still humans, they might mess up, they might have something encoded in a way that they don't expect it to be. And then even when you've read the documentation, or you've gone through a sort of presentation where this data was discussed, it might still be the case that there's some errors in there. And the thing we're most interested in is there a lot of noise? Which means, is there a lot of information that is going to be useless? Some features that through their encoding might be useless, and generally everything that the model will be negatively impacted by. So one of those examples might be anomalies, and by that I mean either that, for example, a feature contains very large values or very small values or very inconsistent values. So for example, if there's some feature encoding money, you see that the numbers are jumping from the thousands to the 100,000s to the millions, which is not in line with the rest of your data. You might suspect that there's something going on with the currency. Maybe someone mixed the currencies, for example. It might also be the case that you have a string feature that doesn't necessarily always say what it intends to because scraping of data went wrong. So for example, rather than director names, you might all of a sudden have actor names, and these things are not uncommon. So always good to check if every feature really contains what you expect it to contain. The second point sort of ties in with this. So are there very big outliers? Do we have a lot of missing values? Are the missing values random? Are they due to some error in the data set collection? Can they be corrected? All these kind of things are important to consider. And then finally, do we need to standardize or normalize our features? Do the scales differ a lot, especially if you have some features that have very big ranges, some have very small ranges, some are discrete, some are continuous. This might very much throw off your classifier or whatever you're using for regression. If you might want to do further pre-processing, these are all very important considerations. Also, definitely not a minor thing to look at is the way that the dataset was labeled, especially if you have a pre-made dataset. So most of the datasets used in academic research are actually hand-labeled. You can, while collecting data, you might use some metadata for labels, but generally when you have a more complex annotation where you might want to, for example, sort of mimic human behavior, you really need people to go in, look at the data, and then make the labels for you. Now this is annotation, and these annotators that are doing the annotation can differ in opinion, in attention, in quality. So in that sense, it's almost essential to look at the agreement scores of the annotators, to look at the individual annotators to see how well they're doing, and definitely look up these numbers because they are commonly reported in papers, in documentations. You want to know how many annotators there were, how much their agreement was, if there were any annotators excluded, if there was a process that selected annotators. All these kind of things will help you assess the quality of the label because you use it as a true value. Basically, you say to the model, this is definitely the label that should be on this instance. And when it's done by humans, it might not necessarily be true. So then your model also has sort of an upper bound of what it can possibly get from this signal, and it will probably have sort of a ceiling in terms of performance. Now, another very dangerous point in assessing your labels is to check for information leakage or pollution or contamination. And this is something that is probably better to illustrate. Say that we have movie scores. So we have the IMDb dataset, and each movie is labeled with a score that ranges from 1 to 10, as we would give the movie some review score. So say this one has a 7, this one has a 4, this one has a 1, and this one has a 3. Now, if we don't in detail inspect this data set and we'll just take this as a feature, as a target, I mean, to make predictions, if we then after discover that there's also a feature that encodes the quality, let's say, of this film, and this is some rating that ranges from let's say B, C, F, E, or something like that. So there's some sort of encoding scheme here, but looking at this you can already see that these sort of map to the target that we're predicting, right? So these are just some number encoding that someone bin this target right here. So transforms this scale into discrete variables. Now this is easily overlooked, but your model will definitely know that these things are in there. So after training on the entire data set right here, using the score as a target, you will probably see that quality is one of the most important features. And then this should spark your criticism of your model, should go into evaluating this feature, probably manually. And if you would look at a plot that compares these to the scores, so say that we check out a bar plot, you will see that there's a perfect relation between the discrete variables here and then the numeric ones here. So you will see that f is almost always 1, and then a is always 10. And there's no a's that, for example, are 1. So there's a perfect overlap between quality and the target. So you might ask, why is this problematic? Because quality is apparently a super informative feature to predict this. If this feature over here was actually derived from this one, then that's not informative at all, is it? There's actual features like actors, maybe money that was spent on the film, so budget, I guess. These are sort of the features that you want to use in general, right? If you want to do predictions for how good a movie will be, you want to look at some features that might be manipulated to generate a good movie. So we want to know, do we need to throw more money at the movie? Do we need to hire Brad Pitt to come and save our movie? And just changing the quality label that is derived from this one will not help at all. So this is, again, what's sort of referred to as information leakage, which is that information regarding your target is actually encoded in your features somewhere in a way that is not random. So it didn't happen by chance that these overlap. It's due to some heuristic or some process where the target and some of the features just encode the same thing because the data set was designed to do this. Now, sort of related to this is looking at how useful your features are before you're going to do any type of machine learning. The thing we don't want to do is throw away features that we think are intuitively uninformative, or only include the ones that we think are very informative, for example. Because there might be some relations in these features that you as a human don't necessarily see, but some algorithm is going to find out for you. However, it's always good to sort of assess the importance that your model places on some of the features and see if they align with what you think are informative features to this problem. This will not only help explain the behavior of your model, it will also sort of show you what actual surprising features are. And for this, you need to know your data set. You need to know what the features are. If you're working with, for example, some biomedical data, it's important that you know what the observations are so that you can interpret the results, that you can interpret your model. All these kind of things are important when you're doing this type of research. You don't want to just show metrics. You really want to interpret what's going on. While inspecting your data, you might also find that you need to make some considerations regarding your target. And one of the most important ones is, do I actually have a target? So is there something in the data that I think allows for prediction? And is this variable that I'm using something that I can actually do useful predictions with? and especially the useful part here is important to consider. The fact that algorithms allow you to try to make predictions doesn't necessarily make them useful. And then the next one to consider is the task that I think I'm going to do, is it realistic, in a sense that do I have enough information in my data set to predict this target? For example, say that we want to predict the mood of a person given a single message that they posted on any social media. Obviously, this is not going to contain enough information to really ascertain something that is as fluid as your mood. So try to sort of assess, is what I'm doing, is it actually realistic? So looking at related work or any theory or anything from literature that you might be able to use to motivate certain signals and certain targets is actually a pretty good way to go about this. This also ties in with the next point. By are you doing what you want to be doing, I mean, is your prediction task that you've set up with the data that you have enough to really sell what you think your predictions are? So say, for example, we're doing some predictions of housing prices in a certain neighborhood. We wouldn't want to sell this model as we can predict the housing prices of the entire country, because obviously these are going to have a lot of different circumstances. Generally, you would want to avoid this kind of presenting of your work as the solver for everything that you think you are doing. So take into account what your data sample is and how that might affect your predictions, what the sort of external factors are, what you do have in your data, what you don't have in your data, what your model pays attention to, what it doesn't pay attention to. All these kind of things will try to confine or sort of zoom in your setup as much as possible so that you don't claim to have a solution for something that you do not necessarily have. And most importantly, are you measuring the performance correctly? We already talked about this, so do you have the metric that matches the thing that you want to do? And in relation to what I said just now, your data is obviously a sample, so you don't have access to the entirety of observations that you might possibly have to do a prediction. Otherwise, you wouldn't have to do predictions. But it's also good to consider this when thinking about how your data and your target are going to be informative to your model. So, for example, when doing anything with language, is the language that you're capturing something that is general for the whole population? Does it only hold up for a certain age group? Is it specific to the platform that you're getting data from? So written text obviously looks way different than social media messages. And also, is the sample representative for the general statistics that you would assume? So do you have a correct balance for example, age? Is gender equally represented when predicting housing prices? Do you have a normal distribution over the housing prices where there's few cheap homes, few very expensive homes, and a lot of mediocre priced homes? All these kind of things are important to consider before actually getting to work. Now, when you've inspected your data, you're confident about doing some sort of research on it, you have a research question or some task that you want to be doing, I think the foremost point to consider is, do I actually need machine learning for this task? Do I want to do predictions, or do I want to show that something is the case? Because these are very different forms of data science. Just proving something is the case using a very big data set doesn't necessarily need machine learning. You can go very far just by showing good aggregations of data, showing plots, having some sort of qualitative analysis of the data. You don't necessarily need to apply it because it's hip now. You apply it because it's the right tool for the job that you want to do, and you hope that it will give you additional insights, but it's not a one method to rule all the other methods, right? It's really something that you need to be confident about applying, because you will waste a lot of time if in the end everything turns out to be useless, and a simple analysis would have done. So once you've decided this, we can go into picking which algorithm fits our problem. Now, one of the traps a lot of people fall into is either thinking I need to mathematically understand all the models to apply them, or on the other side, I don't need to know anything about the model to apply them because they're just black boxes anyway, and I have my nice metrics to show that they're working, yes or no. I think the truth is somewhere in between. You need to have a certain notion of what the algorithm is doing, because that will explain a lot about its behavior and when it's working well and when it's not working well. And these are the things you are considered with, right? The evaluation is very important. You need to want to make decisions how to improve performance of your models, and you can't do that if you don't know what it's doing. Similarly to the point right here. So how will certain hyperparameters that the model has affect a certain point in the evaluation that you want to do? So is it going to fit the data more tightly, which you probably don't want to if you don't have a large data set? Is it going to throw off the entire vector space into some direction that is totally not necessary if you don't have a very complex data set? So having some surface levels intuitions of these things is a bare necessity, but a very deep understanding of the math is definitely not necessary. In addition to this, for some of the use cases, it's also important to consider how interpretable an algorithm is. And by that we mean how well does it show what features it's paying attention to, and how well can we assess the decisions it's making. So it's reasoning. For most of the models that we explained during this course, this is in different degrees applicable. So I'll just show you. For example, when we're doing classification with decision trees, as you know, we have these decisions and they will literally reflect a rule set that can be used by a human after a model is trained. So we have these if certain feature, yes, no. Not only will this reflect the most important features to the model at the top of the tree, it will also give this rule set. More specific rules are the edge cases are usually way at the bottom, and those might also be interesting to analyze. Now, when we're looking at K and N, where we just have this space with points, and it's remembering all these vector coordinates, and then making a decision based on neighbors, it's not as easy to sort of show what the important features are, but you can show what the most important properties of the neighbors are. So we can inspect what the closest neighbors were, we can look at their vectors. See if they have some information in common. And then based on that, sort of inform ourselves why this decision was made. Now with logistic regression, we obviously have the coefficients that we can rely on. Any of the features will have some importance, and we can interpret these weights that were placed on these features to come to a certain conclusion, and then inform ourselves what the model thinks, given the current data set, are important features. So these are all sort of bare bones interpretable algorithms. Now further down the course, we will see that, for example, if you're using SVMs or neural networks, and especially SVMs with nonlinear kernels, this will become very problematic because they're pretty difficult to interpret. They make some complex calculations, and therefore their output or their sort of representation of the data is not humanly interpretable and needs a lot of steps to come to some sort of intuition about what they're doing. And then finally, how is our model performing? Does it have a lot of bias in different predictions? Is there a lot of variance? Is it underfitting? Is it overfitting? So, for example, is our training performance very low and then the validation or test performance very high, or the other way around? Can we look at the sort of fit of the model, especially with logistic regression. This is sort of easy where we can actually see the fit of the model. So is it fitting very tightly these instances that we have? Is it a bit looser? Is it too loose? Is it not following the trend that we're expecting? For decision trees, is it making a lot of different nodes that are useless, that only classify a few examples, will probably not generalize very well? For KNN, is it taking into account an amount of neighbors that is too low and therefore doesn't generalize well, because it very tightly fits the data where maybe it shouldn't, because the groups that we have in this space are actually many. These are different forms of overfitting or underfitting for these different types of models. And it's important to try to get a sense of not only how your model is performing in terms of the metrics, but also in terms of any type of qualitative analysis that you might apply onto the model, where you try to assess these properties that might indicate either underfitting or overfitting. And then finally, because the metrics are so important, we really want to make sure that we have fair evaluation, which is, I think, one of the more easier things to do. It just requires following certain steps, choosing a good evaluation scheme, and you're basically set up as good as you can. But there are some trade-offs that make it a bit more difficult than just following some rules. So we'll get into those evaluation schemes a bit later. First, let's make sure that we have everything in place. So make sure that we have a baseline. Now this can be, for example, majority class for classification, where we just look at the most frequent one and make this sort of classifier that always guesses this majority label for all of the test instances that it sees, and see how well we're doing. For regression, we will just look at the mean, so we'll always predict the mean value from the training set for all of our test instances. These are very dumb baselines, right? They don't do anything, they just look at distributions. Usually it's better to make your own, so especially if you have an interesting problem where you think, okay, so as a human I would look at these few things, then make sort of a baseline that tries to mimic your intuition regarding this and try to beat it with a good model. Or alternatively, if this isn't really possible, you can always go for a very simple vanilla algorithm that isn't tuned or anything, or is just a very simple type of model. Decision trees have a lot of very complex variants, but the simple ID3 or a J48 decision tree is a good sort of baseline method. KNN also very strong baseline to beat. If you want to do more fancy models, these are definitely the ones that you would want to pick for your comparisons of doing better than just sort of standard implementations. And the final, most important one, leave your test set aside until the very end, because this is your fake new data that you don't have access to while training or tuning, and it's there to indicate if you're doing well, yes or no, if your model generalizes. If you've gone through the whole pipeline, trained, validated your parameter settings, done all the evaluation steps well, and your training data performance is still bad, this is the point where you might want to consider different algorithms, more data, better pre-processing to reset the sort of pipeline that you're running over. We'll get into this a bit later, but this is sort of the point where you can say, okay, I'm going to change my approach, and then you can look at the test set again at the end. But in general, just keep it aside as long as possible, and definitely don't tune anything looking at the test set performance and how certain things affect it directly. Okay, so I will now go into detail a bit more about these evaluation schemes. Just to draw it out, usually it helps, don't know if it will help you, but it always helps me to just try to visualize the things that we're doing. So, as you've probably read by now, holdout is a way where we manually split our data. Now, holdout data might have a different sort of meaning, but in general, the holdout evaluation scheme is where we split manually. So other than having a train test split, we also have a validation split to, if we want to do any sort of parameter tuning, we need a validation set. So these are the three splits that we'll have of our data. And they can have certain percentages, which are sort of, they're not set in stone. Generally, you might want to, for example, use 80-10-10 or some lower percentages, but definitely validation and test are usually smaller than your training set. Now, in terms of having our entire set of data, and then our target right here, the holdout method will chop this up into the percentages that I showed. So will look something like this. So this will be train, this will be val, and this will be test. Then we have our model, and our model is going to train on the training set. And again, realize that model is an algorithm plus parameter settings. So if we have different parameter settings in the holdout setup, we always train on a training set and we test our one parameter setting on the validation set. So say we use KNN, we say K is 3, we memorize the entire training set and then see how we perform on this validation set as a sort of fake test set. So reading about cross-validation, you will usually see that the folds are actually train and test. Just keep in mind that while doing parameter optimization, this is generally referred to as the validation set or development set or whatever. You test on this, but it's not your test set, right? Our test set we want to keep separate of this entire process. Okay? So say that we have case 5. Case 5. We also train and then test again. So we will have a performance for case 3. We will have a performance of case 5. Those are all tested on the validation set, and then at some point we take the averages of our parameters, parameter scores. So not the average of the parameters, but the average of the scores, and then we pick the best parameter. And then we test them on the test set and we get our final performance. So one of the problems with the holdout method is if you don't have enough data, the chance that your validation set will be biased, so this is a different kind of bias than prediction bias, this is dataset bias. It might be the case that your validation set has a different distribution of instances in terms of their targets. So say that our training set looks like this. Our validation set might actually look like this or something. So it's definitely not the sort of same distribution over Y, so it's somewhat biased. However, it might also have a different distribution over features. So similarly, for any X, so let's say X2, so feature 2, the distributions might be different. This is something we don't want, right? We want hopefully them to have the same type of distribution. Now, this is easy to accommodate for. We can just stratify, as this is called, our data to make sure that there is an equal distribution of labels in these splits that we do, but for features, it's less easy to do. So to avoid this sort of bias in our data, we can take different countermeasures. However, it turns out that given enough training data, the size of your validation set will be large enough for these to sort of come together. Any of the other measures, such as cross-validation or leave one out, are actually very time expensive. You repeat these steps a lot, so it will cost you extra training time. And even though you might do them multi-threaded, it's still quite a time investment, especially if you want to do nested cross-validation. So if you have a lot of data, this will take even longer. So luckily, the more training data we have, the less we actually need cross-validation, because these distributions will approximate each other a bit better. However, it's hard to say when you have enough data to rely on holdout only. Now, in the end, this is only going to give you better generalization and better performance. So if you have the luxury of time to do cross-validation, definitely opt for cross-validation. If you have even more time, definitely do nested cross-validation. However, if you have some deadline or whatever, you might want to consider not doing these, and you will probably have lower scores as a result, but at least you would be able to actually train your algorithm, which is, I guess, a bit more important than just doing very, very nice validation. But remember, this is under either time constraints or resource constraints or whatever. In general, we always prefer these. So let's go into cross-validation. Now, cross-validation is basically the holdout method, but then repeated, where for each fold, as we call it, we have a different division between training and validation data. Now, by different division, I mean they don't differ in percentages, but they differ in which part of the data set we use as training and validation. So remember, our test set is way to the side of this. We don't care about our test set for this particular thing. What we do care about is our training and our validation. So train and test. So this would be a standard holdout setup. Now let's assume that we do k-fold cross-validation with k is 5. So that will be 5-fold cross-validation. So we'll have one where our test set is here, one where our test set is here, one where it's here, and then one where it's here. And then obviously the rest will be train. So this and this part will be train. This part and this part will be train. This part and this part will be train. And then finally this part will be train. So test, test, also test, more tests, and then these are all training. Now what this will do is that any part of our data has been tested at some point, and every part has been trained at some point, and it's going to generate 5 scores for us. So let's say we're focused on accuracy. We have 90% accuracy here, 85 here, 90 here. We'll have, let's say, 65 here, and then 90 here. So this will give us some average accuracy score, but it will also indicate which parts of the data are apparently harder to train. So fold 4 right here is apparently a bit more difficult because we have a lower accuracy score here. Now, if we do this for more models, we'll have more scores. So let's say this was KNN, and now we're going to do decision tree, and then we'll have comparable results. And now we can do, for example, a t-test to compare these two. So how does nested cross-validation look like? It's basically the same, but for each fold that we have, so let's say we do 3-fold CV just to make this a bit easier. So we'll have 3 data sets. Or 3 splits, actually. These are not different data sets. Same data. Just that this is test. This is test. And this is test for this split. So this is fold 1, fold 2, and then fold 3. And with nested cross-validation, what we do is that we tune our parameters based on the inner folds, and then we choose between different models on our outer folds. So per fold, we're going to have a an additional split of only the training set. So we take this one for the nested part, and we're going to split up this one again into 3s. Then we tune our parameters on these. So we get 3 scores for a parameter setting. Say that we do K and N. So case 1 will have 3 scores. Case 2 will have 3 scores, etc. And then we pick the best one for the inner fold. And then with that parameter setting in the outer fold, we're going to do these. So we'll have, with this parameter setting from this fold, chosen from the inner one, we have, say, case 2 was best for this fold. Case 3 was best for this fold. And case 5 was best for this fold. Now this means that we have an unstable model, so this is definitely not ideal if there's different Ks for each fold. Let's have majority here, so let's say we have case 2 here. So case 2 has been the best over all the inner folds. So for this one as well, and for this one, for this one it was 3, but for this one it was 2. So we end up with case 2, and then we evaluate case 2 on the outer folds, and we get some performance. So for case 2, we also have 3 scores. Now this allows us to, if we use a different classifier with different parameter settings, to also have a best parameter setting based on the inner folds. And then for the outer folds, we have say we have some pruning factor for decision trees. We also have 3 scores. So rather than the parameter settings being tuned and then we evaluate the best parameter settings between each other, so only having 1 score, we now have a set of scores to compare, and we can again do this with a t-test or just take the average, whatever strikes your fancy. Now leave one out is exactly the same thing as cross-validation, but with the amount of folds being equal to the amount of instances that we have. So for each huge chunk of training data, we are only going to evaluate on 1 instance. So as you can imagine, we need to repeat this very, very, very many times. So leave one out is actually only useful when you have very little data and you need to maximize the amount of training data that you have. So I'm not going to draw this out, obviously, because we'll have 1 instance for all different training splits. But you can imagine repeating this as many times as you have instances is going to cost you a lot of time. So to recap, holdout you can use if you have a lot of data or you have limited time. Cross-validation you should generally prefer doing, especially nested cross-validation, unless you don't necessarily have the time. And then leave one out you should only apply if you have either an incredible amount of time for very little data, so that it doesn't cost a lot of time and you can sort of maximize the amount of training data that you have. So let's apply this in a real example. We will see some underfitting, some overfitting, and generally in a real example, hopefully this will help you sort of frame all these things that we're talking about. Just a small disclaimer, these are not rules to live by. I'm just going to go through the approach, how I tackled this data set in a very short amount of time, just to prepare this example. So these are not necessarily steps you should follow by heart. This is just me trying out some things. Actually, different data sets determine a manifold of different things, as we've seen before. So don't think that this is the guide to do regression at all. Anyway, this is just here to give you some more visual demonstration of how these things go. So let's start with our data. I have a Kings County housing data set from Kaggle. It has a bunch of features. It has a recording date, a price of a house, it has the amount of bedrooms, bathrooms, square foot living, square foot of the lot, the amount of floors, if it has a waterfront, there's a view, the condition of the house, some grade, some other square foots, the year it was built in, the year it was renovated, the zip code, and the locations, and some more square feet. So the only thing I'm going to get rid of, obviously ID isn't used as it's the index, the date is not really useful, so we'll throw that out, and then the rest we use as features. Now the thing we haven't gotten into in the practical yet is pre-processing data. This is going to remove price here, set it as our target, convert the rest to a matrix. Now I'm going to do a scaling operation to standardize the data. This we'll get into later. I'm going to split into, and this is pretty important, I'm going to have a hidden data set. So this is going to assume that this is actual real data, so that these will be houses that we'll have to classify in the future. So this is not your test set. I'm going to assume that I just literally don't have access to this data. I can't even evaluate the performance. So anything I will do afterwards is going to be a sort of prediction of how well I did in the future. If I would have told anyone deploying this model, this would be the best model. Also, I'm going to generate a bunch of interaction features, or polynomial features as they are called. So I fit these only on the training set, or our actual data, and then just apply the same transformation on our hidden data to make sure that I don't use any information from the data I don't have access to. But this is less important, so let's go to the next one. So the first one we'll start off is just a basic linear regression model. There's not much we can do with this. We can't really tune it that much. I mean, we might, but I'm not going to do that here. So I don't need a validation set to evaluate any parameter settings. So I can actually train on the full training set. I'm going to use a closed form solution. So I'm just going to calculate the best fit here, and then I do predictions on our set here. I have some predictions here. So this is y hat for linear regression. I'm going to measure the mean absolute error between our actual values and the predicted ones. And I'm off by this much apparently. So this is in dollars. So I'm actually off by a lot, but as you can see here, mean absolute error of the mean for all the values. So this is just the mean score. We just predict mean for everything. That's what this small function does. You don't need to really understand what it says here, but this will give us a baseline, which is even further off than this one, almost by twice as much. So we're actually doing pretty fine with our linear regression model, better than just predicting mean. Now, obviously, if I would have settled on this model right here, then we'll deploy it and see how it goes afterwards. So this is not something you should do. This is just for this example's sake, that we can actually see how well it performs in the future. So let's apply it to our hidden data set right here and see how far we're off. So actually with 120,000 something, we are pretty close to what we thought we might get. So these performances are very, very comparable, which is super good. I'm very happy with that. But as you can see here, if we look at the density over the prediction, so this indicates that some predicted value is more apparent within this range of values than it is here, we can see that the true prices, which are to the left here, and then the darker line are the holdout prices, those follow the exact same distribution, right? Which they should, because they're from the same data, so they don't vary that much. As you can see, our predicted prices, so I wrote here biased predictions because you can sort of see that this is a strong bias towards a lower density of values, so it's more spread out, so to say. And then the holdout predictions are pretty much the same. So from this we can conclude that our model is pretty biased. It consistently predicts another sort of distribution over our labels. So here you can see a nice display of sort of bias in a visual sense. Also more variance, because not only is it offset, it's also lower, so it's more spread. Now we can sort of inform ourselves with this plot what's causing this. So you can see this is 0, so not many houses will probably be in this zone right here, which we can also see if we look at the true prices, so the darkest line right here, and then the holdout prices right here. You can see that there's some cutoff here. There's no houses that are cheaper than this price. However, our model does actually predict lower values, and as you can see, we'll see in the next example, it also predicts negative values, which, while we might think that the model is actually performing well, I mean, we don't want to have negative values, right? So we can already see some sort of heuristic that we would want to build on top of this linear regression model that we have, that it only predicts houses from some price, and then we'll upscale all the other ones, which will probably reduce our error. But again, I just use some naive implementation, vanilla regression. So let's try a different model. This is a combination of a kernel trick in combination with rigid regression. Don't need to know what those are, just describing what the regressor is. So you can use sort of different kernels as in SVM, as you will see somewhat in future lectures. We use a radial basis function kernel, then we do our predictions, and we see how well we're doing. So recall that we're interested in comparing baseline with sort of vanilla models, and then what we assume will be a better model. So we just visualize this in this table over here, then we can do the comparisons, and we can actually see that at least on the training set that we have, again, I'm not doing any tuning here, so there's no validation set. But we can see that this is actually doing worse than our linear regression model. But again, we're beating the baseline, so that's pretty good. Now again, this is data that we generally don't have access to, but for the sake of this example, it's pretty interesting to look at this 50% data that I removed that we don't have access to, and just want to see how we perform. So our super test set. We can see that the distribution is actually different from the one that we had before. So rather than undershooting sort of the density, we actually overshoot it. Again, we're biased because we're off somewhat from the mean house prices that are actually in the data. There's more prices here than there should be. It's a bit wider than this distribution right here. What we can also see is that it somewhat goes up around 0, which is somewhat weird. So this might indicate that the model is actually not really taking into account the observed values, but it's just learning some function that also offsets the prices here in a way that it shouldn't. However, if we compare our hidden performance, we're actually doing pretty okay. So compared to the previous one, where we had 126,000, we now have 129,000. So as I listed here, these are the performances on the hidden data set. We're not off by a lot. I just wanted to show you a very quick example why you should never tune on the training set. Very important considerations. I just take the kernel ridge regressor here again, and I'm just going to tune alpha until it reduces the error a lot. Just going to look at the training set and see how it does. So as you can see, decreasing alpha will, for this classifier, it will tighten the fit. This is all you need to know. It's not really very important, but it will scale the instance space so that we have a way better fit. But because we only evaluated on training, this will probably go down even way more until we have the most perfect fit we can imagine. But again, if we sort of visualize this based on the predictions on our holdout set, which is then our hidden set, and this should also not have been linear regression predictions, but kernel ridge. Anyway, we can see that around 0, it actually has this huge increase in predicted values. So a lot of the predictions are actually around 0, which obviously we do not want to. So this here you can see that it's super overfitted. It's totally not really predicting what we wanted to do. More so, it's also very much offset around 0. So this is very weird model behavior, because we tuned it believing that it would decrease our error, but actually it's introducing very, very many errors on on future data. So very good visual motivation of why you should use a validation set to actually check that the parameters that you're fitting are doing things that you want to do. So let's do it properly now. I'm going to do a few things. So one of them is training this kernel ridge regressor using cross-validation. I'm also going to train a KNN model regression. So not classification, but a KNN regressor. But basically in the same fashion, where I just do a grid search. Now, I didn't do nested cross-validation here just because I have time constraints making these slides. So I didn't want to wait a very long time until everything got nicely sorted out. So these are not sort of definitive results for this particular set right here, but it got me sort of through getting the results as quickly as possible. Anyway, so below here you have the results on this hidden set. Here you can see the values I used for alpha for tuning. So these are all the parameter settings for alpha for the kernel ridge regressor. So as you can see here, we have one inner CV because we're actually only doing this parameter tuning. Now this is not necessarily called inner CV. If we only do one cross-validation, it would just be cross-validation because there's no outer one. So why would we want to refer this to inner? But previously I had an outer as well. This is why there's inner here. But anyway, you can sort of see this as related to some inner cross-validation because we only check for the parameter settings. Now, as you can see here, the cross-validated kernel ridge does a lot better than the one that we overfitted, and does slightly better than the one that we just chose the vanilla values for, and it does somewhat better than our linear regression model. So this is actually pretty good. But sort of the winner of this small experiment is definitely our KNN regressor, which achieves a pretty low performance on our hidden data set right here. So we're only off by this much. It's still probably a considerable amount of money. Not really sure. I didn't go into full detail on seeing if it mispredicts the very expensive houses, or this is caused by the fact that it might also predict negative values. This will probably be more unlikely with KNN, but again, I didn't do this qualitative analysis, and this is in general very important. I just didn't have the time here, just looking at some plots, but this is stuff that you should be very interested in after doing predictions, that you analyze what is the model paying attention to, where is it failing, where is it doing well. It's very important to your final analysis and drawing any conclusions. So just to nicely plot the final results, you can also see the comparison between test error and the error on the actual hidden data that we have. So one thing to note here is obviously the very much overfitted kernel ridge does very, very well. These are in thousands, by the way, so this is times 1,000. So it does very well here, but obviously the error here really skyrockets when we actually apply it. So we might have been very confident here, like, oh man, we have an amazing model, it's doing so well. But actually when we apply it, because we didn't use a validation set, in real life it's going to be off by this much, which is a lot. So one of the things to note here regarding our vanilla models is that they do a bit better on our training set. So for these, this would be train, because we didn't have a validation set. And for these, it would be val, because we did have a validation set. So the test error here is actually train and validation error. So notice that these do a bit better on the training sets. So they are likely a bit overfitted on the train, because they didn't have any sort of testing or tuning, so they can only assess this one fit, and then we'll probably have a bit higher error once you actually start applying them, because you will get a different distribution of data. These are a bit biased, as we saw, so these have a little higher error. Now notice for the ones that we trained with validation, even though they have a bit higher error here, at least compared to the vanilla ones, actually they generalize pretty well. So they have a lower error on 50% hidden data, which is pretty good. That's something you should really aim for, this right here. And even better with KNN, because it has a lower error right here, and the performance on our hidden data is best of all of them. Now notice though that our kernel ridge here, the vanilla one, has a lower error on the training set, but it had access to more data, so we'll just blame it on that. Obviously we don't have this data generally to really make sure that we generalize well, so we might have actually chosen for the vanilla kernel ridge given only these options. Obviously there's very, very, very many more regressors. I didn't explore all the parameter tuning possible, but at least this would be our preference based on the performance if we didn't really care about generalization. If we didn't take into account this because it's only fitted on the training data, we didn't really do any tuning, and we would have gone for KNN, and we would have actually been off a bit better. So that was it for this part. Hopefully it will help you to better understand the evaluation metrics and sort of this part of the course. It's always good to sort of test it on your own, but generally you don't have a lot of time and experience to do it, so this is why I prepared some real example for you. I hope this was informative. If you have any questions, please post them on the forum.